the cloud, a magical place called the cloud. Right, so we worked on a simple case involving integration, and it wasn't that bad. I mean, the act of finding the integral wasn't terrible, but in the case of number 2, and we're focusing on area right now, we'll get to arc length, but let's just focus on the area because one thing at a time. And in fact, I'll even take that as a typo because area, like those problem examples should be self-contained. So this number 1 and number 2 should just say find the area, and then a fresh set of examples for arc length. There's just not even enough room for arc length on this, but we'll get to it. All right, but let's take a look at this guy, because as you may have discovered if you try tackling this one, definitely a little bit crispier than the one that we just did. So if you were trying to follow along on what I was doing on Desmos while I was just randomly tapping stuff, magically making things appear, I hit the little wrench on the top, a little monkey wrench or pipe wrench or whatever it is, and you can see that under grid there's a few options. One of them, or a couple options. One is your Cartesian plane, the coordinate axes, and the other is a little polar graph icon. So if you select that one, then you're good to go. You really don't have to worry about anything else. You typically want to have it in radians, just at least as a default. You might have to change it to degrees from time to time, but that's where you would go to do that stuff. So then you can tap out of here, and your graph grid is the way you want it to be. And it's just a matter of getting things on or in the editor the way you want it to be. So in this case, it's alphanumeric r equals 2 plus 4 cosine. So into functions, trig is the first set of options. And then, I'm sure you could find it somewhere. I just don't like hunting around for it. So I just start typing in theta. If I want pi, I type in pi. So then that's all there is to it. You can manipulate the domain. And so when you do that, you can truncate this or you can expand upon it. But since it's a cyclical function, it's just going to follow the same pattern. So the best you can hope for is that it would, overlap with itself. So it'll go through the loop, finish the loop. If you expand on the domain, all it's going to do is trace over itself. I could show you that really quickly. So let's say you have 4, and again, where's pi? It's definitely right on that screen, but if I don't know, I can just type pi and it shows up, all right? But you can see it's the same figure. Maybe 30 pi, same figure, right? Nothing changed. But then if I go to just pi, see, I'm only getting half of it, all right? That's because after it's completed one full cycle, all it's doing is overlapping itself over and over again. So it's kind of like a racetrack, right? So we're not really talking about the path that we're not following the car as it's making its laps. We're just looking at the racetrack, and you can go around it 1,000 times. That racetrack is still oval. All right, so we need to find the area. I say area of, but it's really area contained within this figure. All right, so somehow I gotta figure out the area here. Now this is definitely the trickiest type of question that I could ask you related to polar functions. Not to say that it is the trickiest question in creation. I'm sure there's wonderfully tricky questions out there. This is just the trickiest one that I put on the table as a possibility, right? Because we have our formula, 1/2 r squared d theta. That's fine. What we're going to end up with here, and let me just kind of bring this in. I'm going to do it the old-fashioned way. A little screenshot. And I know some people are more comfortable with the TI calculators, but this is a pretty solid selling point for for a Desmos calculator. So, TIs can handle the just lost my train of thought there. Why is this not showing up the way I want it to? Okay. TIs can handle polar functions also, but this looks pretty crisp and clean, So what we're going to have here is the need to start off at 0 and go around to 2 pi. That's fine. That's given to us. That's obvious, right? But if I want to conceptually start thinking about this area correctly, what I'm going to do is really be thinking about every single circular sector that could exist starting at the pole and going to the outermost part of the figure, so the circumference. All right, so I'm going to just draw like a little subset here. So that would be like, for example, one little sector. All right. So we talked about this last time when I drew the diagram, but this is really what I'm up against here. All right. It's got an R value, and it's got, you know, I'm kind of exaggerating the thickness of it. That would be associated with some value theta, but it's really a d theta. All right. So this is an arc. All right. So this is the arc here. All right. So ds, because it's infinitesimal, is, you know, s equals r theta, ds equals r d theta. All right. So when I'm looking for the area of the sectors, 1/2 r squared d theta, the d theta is coming from this guy. So that's all stuff we talked about. But I'm going to need to go all the way around this circle. Let me get a little purple going on here. I'm going to need to go all the way around the circle, collecting every one of the little circular sectors that could come into existence. So we get another ds over here, corresponding, that's not a ds, corresponding with a d theta. So that's another arc. And we'd have another one and another one and another one. And then eventually we get to the end of the northern hemisphere, if you will. When we do that, we'll be somewhere over in, I'll say, this neighborhood. So like right over in this neighborhood over here. So let's say I got that little sector. All right. So I'm working my way around, all the way around, collecting those areas. But then once we do that, then we got to work on the inner circle. All right, but that's a problem. All right, it's actually a very significant problem that'll skew our results in a major way. So if I start collecting circular sectors within that inner loop, what I'm going to end up doing is double counting that area. All right, because I would have already grabbed the area of that inner loop just by going around that northern hemisphere, you know, the green, the purple, all the way to the red. I would have captured that inner loop. But if I keep going just by the numbers on the interval of 0 to 2 pi, I'm going to accidentally double count that area on that inner loop. So I want to disregard that part. Right, so I want to count for all areas except for that inner loop, because I don't want to accidentally double count it. Now, if I'm finding arc length, I do want to count it because I need the length around that inner loop, not just the length out of the outside. I was going to say perimeter. That works, but circumference is what I was looking for. All right. So what I'm going to do, let's start off with a little trig equation action here. We're going to say r, which is equal to 2 plus 4 cosine theta. I'm going to replace the r with a 0. And the reason I'm going to do that is because that's going to give me the location of, in terms of theta, the pole. It's going to tell me at what theta values this curve hits the pole. All right. So that's going to allow me to restrict my domain, excluding some of the values on the interval of 0 to 2 pi. All right, so I'm going to solve for cosine theta. Cosine theta is going to be equal to -1/2. Subtract 2, divide by 4. Around the unit circle, dang, this unit circle thing keeps coming up over and over again. It's like there's some importance to it. All right. Theta is equal, cosine of theta is equal to -1/2 at 60-degree reference angles in the second and third quadrants. All right, so we're talking 2 pi over 3 and 4 pi over 3. All right, so what I like to do is kind of test out a theory here. What I'm thinking is that what I would want to do, I'm going to go back to black here. I would want to be going on the interval of 0 to 2 pi over 3, and then on the interval of 4 pi over 3 to 2 pi, right? Because I want to exclude the values in between 2 pi over 3 and 4 pi over 3. That's just, it's a suspicion, because it seems like if I'm tracing around the circle, I'll do it with a highlighter. If I'm tracing around the circle, I would start at 0, right? So I'm starting at 0 and I'm going to 2 pi over 3. So maybe that's the, the outer ring, for example. Oop, overshot the mark there. And then it isn't until, so maybe I'm starting here, working my way around, and then getting here, and then that's the first instance. I don't know, maybe I'm starting here. And as I'm working my way around, this is the first time I get to that inner loop. And then I switch over to the inner loop, and then I switch back to the outer loop. I mean, there's all sorts of possibilities here. I'm just going based off of a suspicion / I mean, I already know what the answer is. I've been doing this often enough, but I'm just trying to put myself in your shoes. So what is it likely to be? So how would you know? We just guess, just hope for the best? No, you have your Desmos calculator. Let's see what 0 to 2 pi over 3 ought to look like. All right, so far so good. That gets us to the entry point of the inner loop. So it was my second suspicion, or my third suspicion. I forget which one. It wasn't my first one. All right, and then after that, we're thinking that 2 pi over 3 to 4 pi over 3 is going to get me the inner loop, which I don't want, but let's see how that looks. That's the inner loop, so that's good. I want to take that part out of the process. So good news there. So let me look at 4 pi over 3 to 2 pi. That should just give me the outermost part on the bottom half. So let's take a look. Outermost part on the bottom half. Very good. All right. So what I'm going to do is I'm going to integrate the 2 plus 4 cosine theta as my r value. But remember, the area model is 1/2 r squared d theta. So we got a little bit more than just chucking it in. R squared d theta on the interval of alpha to beta. All right, so that's our rule. So, but I'm going to be using the 2 plus 4 cosine theta in place of the r, but I'm going from 0 to 2 pi over 3, and then 4 pi over 3 to 2 pi. So 1/2 r squared d theta, and then plus 1/2 r squared d theta, but again, the r being this guy. All right, so there's plenty of instances in this course where you're going to have to do algebraic processes by hand. It's really up to you how you want to handle something like this. You know, if you see that there's a built-in function related to the skill that you need to demonstrate, then maybe you can just do it that way. And by maybe, I mean definitely. I accidentally cleared out the thing that I didn't want to clear. I just wanted to scroll below, so I'm just going to type it right back in real quick. 4 cosine theta All right, so I want to be doing the integral on the interval of 0 to 2 pi over 3. Now, if it accepts the r, that's great, but it doesn't always. You know, there could be a conflict, so we'll give it a shot. I misspelled data, so that ends up being an issue. All right. Honestly, I don't remember what the answer is supposed to be. And also, I didn't even remotely put it in the right way, so I wanted to see if it actually gave me the like an answer, but let me put it in the right way. So 0.5 r squared, so let me just pop it. Well, I don't need the parentheses, so r squared d theta. So that gives me one value. And then from there, I can just add on the other piece and see how it goes. All right, but before I do that, I'm just going to check it because I honestly, wholeheartedly can't remember if it's going to accept that that r that I just typed in. So I'm just going to type it in as the function 2 plus, and also I'm worried about the domain considerations, stuff like that. Cosine THETA, small price to pay.
Professor, why is there the plus sign in front of the integral? I'm sorry.
What is the, say it again?
The plus sign?
The plus sign?
Yeah, in front of the
we're going to add the
integral.
two integrals together.
Oh, okay.
So we got two integrals that we're going to take the sum of. Okay, so it did give us the same value, so that's good. That was more for a peace of mind sort of thing, just to make sure that it was going to know that I was referring to that r. There's no reason why it shouldn't have, but I didn't want to take the chance and give people incorrect information, false hope, and so on, and then have it end up blowing up in everybody's faces. The benefit of doing it using the Desmos calculator as opposed to the graphing calculator, the TI, is that I accept Desmos work as work, right? So if, you know, on a test, if you're allowed to use a Desmos calculator, which you will be, I allow you to submit your work from Desmos as work, as a solution to a problem, right? So all you'd have to do is share, create a share link and go from there. I'll walk you through that in more detail when we get closer to the test a little bit. You know, maybe I'll talk about it definitely next class, but yeah, it's a pretty nice little feature of the course, or at least the way I do things, to the point where, you know, like, why not take advantage of that, right? So I can get rid of that second one because it's just not necessary. I just wanted to make sure. So again, function, it's under miscellaneous for some reason. I guess they just throw in everything that's calculus related, and anything that's not stats and trig is just miscellaneous, but that's fine. I don't think of myself as miscellaneous, so, you know, positive self-esteem here. So r squared and then d theta. All right, and so it looks like we have the same value. And really, when you think about it, you should have the same value. It's the same area. One on the top half, one on the bottom half. But we do kind of gain a really important piece of information out of this. And that is the fact that, this can't be overstated. A lot of the rules from function-related calculus carries over to polars, but a lot of it doesn't, right? So when when you start thinking about like, wait a minute, I thought if it was below the x-axis, the area would be negative. That's because the rectangle, when you're finding the area under a curve in coordinate axes, rectangular coordinate axes, the rectangles had negative heights. The R value here is still positive, right? So that's still going to give us a positive area, right? The theta values, we're still going counterclockwise, so our theta values are still going to be positive, right? It's only if we're going in the opposite direction. R values are always going to be positive. The theta values can be negative if we're going around the other way, right? So it is possible to come up with a negative area, but not for the reasons that you would get a negative area in Calc 1, Calc 2, all right? So you run the numbers, you get all the values, you're gonna look at approximately, and you know, you can just kind of crunch it out here, we're looking at 17 and change times 2. I'm just shorthanding it, 763 times 2. Here, we're talking about 35.5. Square units. They did not give us any units to play off of here, so square units. All right, on a test, I wouldn't be concerned with any kind of labels if I didn't give you any context behind it, but if I said that this is a racetrack and, you know, like R is in feet, then I would expect the appropriate units of square feet. All right, so that should help a little bit with setup and things of that nature, but we haven't talked about finding the area between polar graphs, so that's the next concept. All right, so let's tackle that right quick and see where that leaves us. But the calculator is very, very important when it comes to this stuff. All right, you can disregard the theta step if you're using the Desmos calculator, because as you can see from the display, we're not concerned about windows, you know, like X min, X max, Y min, Y max, because we're pinching to expand and decrease in size. And we're not concerned with theta step because it's producing a nice smooth curve every single time. So, you know, in terms of creating a graph, those are things that we don't worry about. All right, but I'm going to create a fresh new one here. And also, you can save your work on Desmos. TI calculator, when you wipe out a graph, the equation of a graph, you wipe it out. The beauty of Desmos is later on in the course, you realize, oh, I did a problem like this already. Oh, I have it saved. I can go back and look at that. Yeah, maybe it's not square root of 9 cosine 2 theta, maybe it's 9 sine 2 theta, but now you're just tweaking rather than reinventing. All right, so the only thing is when you create a new graph, you just got to go through and make sure that the settings are the way you want it. R equals 3 is one equation. Now, I want R equals, so let me show you. Let me show you how this plays out. Square root of 9 cosine 2 theta. On 0 to pi, so that part's fine. All right, so we have two R values here. When we start talking about, like in the next step, if I were to find an integral, there would be a concern about, okay, well, which one's which? Which R is which? You know, so if I were to say the integral involving R, you know, the best case scenario is that it would come back and give me an error. The worst case scenario is that it computes based off of an R equation that I don't want it to, right? So you have a little issue there. But what you could do, throw in a little subscript, if it lets you. All right, so it didn't let me, oh, because it thinks it's a constant. All right, so we're just gonna live with it. That's fine. For this one, we really only needed the diagram anyway. So what you can do down the line, once you come up with your integral, you know, just you might just have to type in that the expression rather than referring back to an equation. right? So at least we have a sense of the relationships here. We know that the outermost equation is the circle, and the innermost equation is Spider-Man's eyes. So now it's just a matter of saying, okay, well, if I take the circle and subtract from it Spider-Man's eyes, then I'll have the area in between the two graphs. And there you go. And then we color it in red and with little stripes, and then we actually have Spider-Man, right? So that's fine. I would like to know where this graph starts. So the circle is fine, but when it comes to the infinity symbol, also known as a lemniscate, for those of you keeping track of that sort of thing, what I could do is dial back my domain. Instead of going 0 to 2 pi, maybe I'll go 0 to like pi over 6. I just want to get a sense of where it starts, right? So now I know it starts at 3, 0, 3 steps in a direction of 0, and then it works its way toward the pole. So then maybe I'll dial it up to like pi over 2. All right, that gets me to the pole. Then I'll go to pi. All right, so then it flips back up. All right, so a little bounce back. And then I'm thinking that it probably goes back the other way, you know, towards the bottom. So let me put in 3 pi over 2. All right, so then swinging back down towards the pole, and then it's going to do a bounce back towards 2 pi. All right, it gives me a good sense of how this thing is going to be structured. All right, that's something that you can do on the TI calculator. I just don't think it's happening as quickly and as efficiently as it happens here. All right. Question?
Is it always like the tiny slivers that we're adding up for the integral? Does it always take it between the origin and the line?
Is that I think you maybe broke up a little bit there. I heard tiny slivers. Is it always the tiny slivers? And then I lost you.
Can you hear me now?
Yeah, kind of. Let me just, I got my volume on max, so I don't know why I'm not. Yeah, okay, so let me just get a little closer so I can hear. All right, go for it.
The tiny slivers that we add up for the integral, is it always between the origin and the line?
It's always between the origin and the outermost part of the curve, yeah.
Thank you.
All right, and so what we gain from looking at this graph just in bits and pieces is that we know, and let me go green for those people. We're starting here, we're working our way around, hopping back this way, and I'll even continue it, and then hopping back this way. All right, so it gives us a little bit of a sense of what's going on. All right, so now we can actually dive into some of the calculations, which is always a good thing. But we also can rely a little bit on symmetry, because if I want to, and I do, I could just figure out this area here. Once I figure out that area, I just multiply it by 4 and I'll have all of them. All right. So what I would want to do is figure out the first instance where this radical function hits the pole. So I have r equals the square root of 9 cosine 2 theta, 9 cosine 2 theta. I'm going to set that equal to 0. That's one thing you kind of rely upon from previous classes. If you're ever in doubt in terms of a strategy, set your equation equal to 0 and solve. Odds are that's part of the solution. You know, you just might not know why you're doing it. You just know that at some point you always have to do that. Most of the time it involves a derivative, so why not? You know, just take a derivative, set it equal to 0 and solve. But here we want to actually take the original function, set it equal to 0. So 0 equals 9, I keep wanting to make a C, 9 cosine 2 theta. Divide both sides by 9, so cosine 2 theta. is equal to 0. Couple of ways to go from here. No matter which way I explain the next step, it's solving a trig equation, but no matter which way I explain it, nobody likes it. They always want the other way. So like there's two ways I can do it. I go for one of them. Everybody always likes the other way. So I'm just gonna pick one, and with fully aware of the fact that I'm gonna have to explain it in a second way in a second. Second way in a second, that's fine. So I'm gonna let A equal 2 theta. So that gives me a new model, cosine A equals 0. All right. Based on our knowledge of the unit circle, we're thinking about where cosine would be equal to 0. Cosine is the x value. X value is equal to 0 whenever the function hits the y-axis. The unit circle hits the y-axis. All right, so that happens at pi over 2 and 3 pi over 2. You know, also negative pi over 2 and 5 pi over 2 and 7 pi over 2. So basically all odd coefficients of pi over 2. All right, so we have that information. But what I want to do now is go back.
Obviously, Captain America. Yeah, it's a shame Bucky and Cap were at odds for so long. They should have just knocked him on the head real good. That's the scientific way to get people to remember who they are, right? Or you can use a cosmic cube to rewrite their memories. That's what Captain America did to save Buck.
I know that's Cartoon Network. I just can't tell. Is that sounds like Squidbillies or something?
Wasn't the same man who went into
not really sure.
Waters. His remorse for his crime.
Yeah, thanks. All right, so I'm going to divide by 2 because we know that A is equivalent to 2 theta. So theta would have to be pi over 4, 3 pi over 4, and, you know, if need be, 5 pi over 4, 7 pi over 4, 9 pi over 4, and so on. But what I want to do is I want to use my resources because, you know, like, I don't know, like, why are you taking my class? Why are you taking me as your professor? Some of you, because the time fit and there was no other way around it. And some people are like, oh, because he uses technology, and some other teachers don't let us use technology. And if I'm going to let you use technology, then use the technology, you know? And so that's the moral of the story here. So if I want to go and get a sense of what domain is going to get me that like half closed eyelid, then I have some possible values here. Let me start putting them in instead of just kind of guessing and hoping for the best. And that one, the pi over 4 is my winner. That's telling me that if I integrate over the interval of 0 to pi over 4, that's going to get me that one little region. And I know if I multiply that by 4, we'll get where we need to go. All right. There is an issue with this kind of problem because the movement around, it does kind of cross over, even though Desmos graphed it one way. It doesn't necessarily always follow the rules. And so you just got to be careful. The best bet when it comes to polar coordinates in order to avoid negative integrals, integrals resulting in negative values, is to just chunk it so that you grab the part that's in the first quadrant and then rely on symmetry to get you the rest of the way. All right, so I'm going to put 0 to pi over 4. All right, 1/2 r squared d theta. All right, with the r being the root of 9 cosine 2 theta. And then I know that I'm going to have to take that value and multiply it by 4. All right. The other part is the r equals 3. Now, I'm going to be a little lazy here and just say, well, C above, because we already figured that part out. The whole circle has an area of 9 pi. So we already took care of that part. So I know that once I come up with this computation, I'm going to subtract it from 9 pi and I'll have my answer. But before I do that, because I promised an alternative way of solving the equation, I'm going to go back to my 0 equals 9 cosine 2 theta. So this is another way of doing it if you didn't like that first approach. So this is an or situation. You would never have to show both methods, just you may look at this other method of solution and say, I like that one a little bit better. It makes more sense, right? So again, next step, solve. You get cosine 2 theta equals 0. That's fine. You could involve double angle rules for trig functions, all right? The drawback is you got to know what the double angle rules are. If you don't know them, then this method is a non-starter, all right? So there's 3 variations of the double angle rules, and some of them are more helpful than others. But basically, any variation that involves only one trig function, you're fine. There's 3 of them. One of them is cosine squared minus sine squared. That's not the best one to use here. You can use 2 cosine squared minus 1, or you could use 1 minus 2 sine squared, right? I'm going to choose 2 cosine squared theta minus 1 as my substitution, right? That's a double angle rule. This isn't a typo, but I need a reminder, otherwise I'll forget. So I'm going to give a typo bonus point. I just need somebody to remind me to put the trig reference sheet on Blackboard, right? Because it has all that stuff in it, so that you can refer to it. Because this kind of looks like, oh, right on cue. This looks like pulling stuff out of a hat, and it's all stuff that in theory you should know, but I can honestly say that this isn't stuff I really remembered until I became a teacher, so it's understandable if you don't all remember it. I'm going to solve for cosine squared theta, add 1, divide by 2, so 1/2. I'm going to take the root of both sides, so that's going to give me cosine theta is equal to plus or minus 1 over the square root of 2, but that's the same as plus or minus radical 2 over 2. All right, so if you know your unit circle relationships, again, back to the unit circle, you can't get around it. All right, you got this far, maybe faking it, but now the honeymoon's over. You gotta know it. All right, radical 2 over 2, positive or negative. All right, that's all 4 quadrants. 45-degree reference angle. All right, that's pi over 4 reference angle. So any angle in one turn of the unit circle that has a denominator of 4. So pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. We didn't need all of them. We just needed the first one. So either way, we're getting there. Now, again, all I'm saying here is that if you didn't know, if this looks like it's too foreign for you, like, I never would have figured out how to do that. No one's saying you had to do it. But if you know your double angle rules, then this might be a natural approach for you. Okay? But it's neither here nor there. We have an integral that we got to tackle. This one, it kind of makes sense to do a little housekeeping first. Even if we're going to type it into Desmos, we still want to make sure we clean it up a smidge before we go after it with brute force. So we got a 2. I'm going to go navy blue for those keeping score at home. So 2 goes into 4 twice, so that's something. But we also have that power of 2 that can cancel out the radical, and then the 2 can come back into play. So we can clean this up. You got 0 to pi over 4. We'd be looking at 2 times 9 cosine 2 theta, which is 18 cosine 2 theta, d theta. Now that's not too crazy to do by hand, because that's just, I call it baby chain rule, because it's just a little correction factor of 2. But, you know, I'm saying you could use Desmos, so use Desmos. You know, it's up to you. If you like doing stuff by hand, that's fine too. I like doing stuff by hand. There are some people that they like the challenge. I like doing it both ways. I like doing it by hand and then feeling great about myself when I successfully did the thing by hand by checking it on the calculator. So it's all good. All right, so d theta. Fat finger strike again. So we get a clean 9, which is kind of like shocking and surprising because it's like, oh, I didn't see that coming, but it is a number that could happen, so why not? But again, it's not the final answer. Final answer comes from the fact that we're subtracting the area of the goggles from the area of the face. The area of the face is 9 pi, so the final answer, I'll go with this orange color, is going to be 9 pi, so therefore 9 pi minus 9. Oof. Brutal. All right, now, I think it's worth taking a minute or two just to go through the integral of this by hand, just because I think that people can benefit from that. So I'm just gonna show it real quick. I know we've done the heavy duty stuff like trig substitutions and stuff like that, but sometimes people just need help with the quote unquote easy stuff. All right, so we got this definite integral, 18 cosine 2 theta d theta. So the way I handle a problem like this, because you could do it with use substitution, but it really just amounts to, like I said, a correction factor, a numerical value that corrects the expression. So I look at it and say, all right, there's only a coefficient, a linear coefficient in front of the theta. So my integral is going to be 18 sine of something. That something is going to be the innermost function. It's going to be 2 theta. But there will be some correction value, all right? Some number that I have to multiply this function by, or this expression by, I overuse the word function, in order to make it equivalent to 18 cosine 2 theta, all right? So what I would do, and this is like, I mean, probably the most streamlined form of guess and check, is I would say, okay, well, what is the derivative of this thing I just came up with? All right, it would be 18 cosine of 2 theta times 2. All right, that extra times 2, I don't want that. All right, so what I do is I correct for that. That extra value that I would get through the differentiation process, I offset that by multiplying the whole thing by 1/2. All right, this way I get 9 sine 2 theta, and when I check this by differentiating, I would say, okay, the derivative would be, we got constant multiple, 9 cosine 2 theta, derivative of the inner function would be 2. 9 times 2 is 18. That gets me where I want to go. All right, now this is happening over the interval of 0 to pi over 4. So the rest is just fundamental theorem. So 9 sine of 2 times pi over 4 minus 9 sine of 2 times 0. The 2 times 0 is going away because sine of 0 is 0. So this whole part wipes out. 2 into 4 is 2. Sine of pi over 2 is 1. That's going to give us a 9 as a result. So that all leads, oh man, I cannot do this. All right, that all leads to the 9, which again, subtracted from the 9 pi, gives us the thing that we wanted. All right, 9 pi minus 9. All right, so, you know, it's a little bit of extra stuff there. Did you need to sit through that? Probably not in most cases. Some people are like, oh, you said calculator, I had you at calculator. And that's fine too. But just having a little moment where you can take a second and review some of the old stuff is never a bad thing. All right. The next page is just more of the same. Like I said, we'll do arc length, but I don't want to I don't want to steal the examples that I already created for areas. So what I'll do is next time, I'll have a fresh set of examples that we'll use for arc length. I'll post up a document online and we'll work through that, because there was just enough room for the area. If I try to squeeze arc length in there, it's going to be a disaster. Arc length's much easier, but it's worth getting into. So the next 2 pages is a lot of extra practice. Question?
Can you go to the previous page, please?
Yeah, sure. So the next couple of pages is all like a ton of practice. We're not going to go over all of them in class just because there isn't enough time. But the answer keys are online, so you can take a look. And I'll go over 1 or 2 of them. But next class we'll move on to arc length. So
on the solution, if you multiply 1/2 times 18, never mind. Thank you. So,
this work would we have to show with Desmos?
say it again.
How much of this on a test would we have to show?
As much as the directions ask you to show. Sometimes the directions will say, give me the answer, and sometimes it'll say, show me every tiny little detail. So
If we use Desmos.
Sorry?
What if we use Desmos?
If you use Desmos, just again, be mindful of the instructions, because the instructions will say you could use any technique you want, and some of them are going to say you got to do this one by hand. So just read the instructions and you'll be fine. At least in terms of what the expectations of the questions are. I can't speak to content knowledge, but so I just wanted to take you through one last little thing. See, there's a ton of practice next 3 pages. I said 2 pages, but next 3 pages. I just want to take you through one last thing, and really it's just getting you set up with the idea of the derivative of polar functions. I'm not going to actually take you through an example. I just want to kind of get you to the formula, the dy dx formula, and then go from there. And then actually I'll obviously let you go because we're getting to the end.